Okay, so here we are in 6.2. This is going to be our part 2 of the notes. We're starting on page 13. We finished in class, we finished taking a look at this first example where we were considering a function written in unit step function notation. And we rewrote it as a piecewise function, making it a little bit easier to understand. And of course, we can also visualize what's going on here as a graph. So for our purposes in this section, we're going to be making use of the unit step function in algebraic notation, and then of course trying to make sense of what it might mean or what it might look like in these other notations. So we'll take a look at another example here further down the page where we want to write a Heaviside based function as a piecewise function. So what might help is to kind of imagine what's going on. So notice we have two Heaviside functions. So there's something happening at t equals 2, and there's something happening at t equals 5. So we have a situation here where there's a change happening at those particular time values. So right away we know our function f of t written in piecewise notation is really going to have three parts. There's going to be the part where everything is below t equals 2, so everything less than t equals 2, and then there's going to be the in-between time where t is between 2, so it's greater than or equal to 2, but less than 5. So remember, it's always less than, but not less than or equal to. And then last but not least, where t is greater than or equal to 5. So really it's a question of what's happening in these three regions. And so before t equals 2, this thing is off and this thing is off. They're both zeros, so we can kind of ignore these two terms. So up to that point, this thing is going to behave like 3, right? And you can see that in the graph by taking a look at this part of the Heaviside function. Everything else is off, so we don't have to think about those. And then, of course, at a point, so we're going to take a look at what's happening in between these two values. So when the t equals 2 gets turned on, we'd have 3 minus 2, and then this guy is still off. So 3 minus 2 is just going to behave like 1. And that corresponds to, so if this guy right here, that's the blue circled part, then we'll take a look and try to imagine the red circled part. This is what happens when you consider these first two parts. And then last but not least, when all three parts are considered, then anything that's greater than t greater than or equal to 5, this thing would be switched on, but so would this. So if this thing is switched on exactly, you'd have 3 minus 2, so that's 1. And then exactly at 5, this thing is going to behave like 5 minus 1. And at 6, it'd be 6 minus 1, and then 7 minus 1, and then 8. So this is going to change with respect to time. But all of it together, this would just be 1 plus t minus 1. So in other words, it's going to behave like t. And that's coming from all three parts of all three terms of the function up here. Right? So when all three parts are accounted for, when they're all turned on, anywhere 5 or greater for the t value, this thing is going to behave like 3 minus 2 plus t minus 1. So 3 minus 2 minus 1, that's just going to be t. So what would this look like if we were to graph our function? Well, if you imagine, here's a t value of 2, and here's a t value of 5. That's our t-axis, and this is our f of t values. Then at a value of everything before t equals 2 would behave like 3. So it's going to be up here at 3. And so it would be tooling along 3, and then all of a sudden at 2 it just kind of stops and drops down to a value of 1. And so Here's 1. And so it'd start here, and that would continue all the way over to 5. And then it's going to behave like the function f of t equals t. So f of t equals t means you're going to have some extra bit up here at 5, and at 5 comma 5, the point 5 comma 5, you'll all of a sudden have a function going off like that. So it's going to behave everywhere before 2 like that, and then between 2 and 5 it jumps down to 1, and then at 5 it jumps up and then behaves like the function y equals t, or f of t equals t. So we can think of it in Heaviside notation, we can think of it in piecewise notation, we can think of it as a graph, but we should be able to translate between all three of these. So down at the bottom of the page we have another example. It says to write the following as a piecewise and a Heaviside function. So notice it's basically giving a description, telling us how it behaves, and then asking us to write it as piecewise and then write it as a Heaviside. And if we're describing how it behaves, then it's probably going to be easiest to write this as a piecewise function. So for starters, we'll write it as a piecewise. So f of t, let's see how many parts do we have. It behaves like this until then, and then it behaves as something else. So it's only going to be 2 parts. So it behaves as 3t squared until t equals 1. So 3t squared until t equals 1. So t is less than 1. After which it behaves as y equals 2. So it's going to be 2 everywhere that t is greater than or equal to 1. So we have our piecewise notation. Now it's just a question of how do we convert that into a Heaviside notation. So piecewise over here, Heaviside or unit function notation over here. So we need to be able to write this in line in a way that makes sense. So what I'm going to do is I'm going to ask you to hit the pause button and try to work this out on your own. See if you can figure out a way to make a Heaviside function that works. I'm just going to keep going, but you can hit pause at any moment to try to work it out. It makes a whole lot more sense if you try to figure it out on your own. So what we can do is say it's going to have to behave like 3t squared until we get to t equals 1. That means it's on until t equals 1. So if you remember our on until a certain point in time, we can fix by doing a 1 minus the Heaviside function. And this is the equivalent of the reverse switch. So it's a on until we turn it off instead of off until we turn it on. So this, if we stopped right here, we would have something that behaves like 3t squared until 1, and then it just disappears. It becomes 0. But we don't want it to disappear and become 0 at that point. We're going to add another term, and the other term is just going to be our step function, our unit step function, times 2. So at the moment that t equals 1, this thing basically turns off, and this thing turns on. So the 3t squared part of it goes away, but the 2 times 1 part of it shows up. So we've got a description, we've got a piecewise notation, we've got Heaviside notation, and of course you can graph it, or you can step into Maple and have Maple graph it. So let me pull up Maple on the screen here, and hopefully we can see how this works. I'm just continuing where the notes left off. So I'm going to do plot, and we're going to plot 3t squared times Heaviside of t minus 1. Oops, I forgot. This first one is 1 minus Heaviside. So 1 minus the Heaviside of t minus 1. Boop, close parentheses. Plus 2 times the Heaviside of t minus 1. And remember, it's t minus 1 because we're we're asking the Heaviside to kick in when t is exactly equal to 1. Okay, so I can close my parentheses, or if I want to kind of force it, I can say I want to pay attention to t equals, I don't know, -10 to +10, something like that. I don't know, something interesting. And we can take a look at the graph. So it behaves like a quadratic, boink, right up until t equals 1. And if I kind of decrease this, if I go from -1 to 10, something like that, then you can see it behaves like a quadratic, and then at t equals 1, it just drops down to 2, and then stays constant at 2. So in other words, it's like having a function behave a certain way up until a certain point, and then flatline. So we can do that in Maple. We can plot it to see what we're doing. And as long as we know how to communicate with Maple, as long as we know how to make sense of all this stuff in Maple, then we can see a plot. We can write it out in Heaviside notation. Piecewise notation is not as easy to do in Maple, but it's possible. We're just not gonna spend our time on it. So on the next page, at the top of this next page, I identify the relationship between the way we're writing it. This is the way we write it, written, and this is Maple notation, right? And so they're completely 100% interchangeable. Sometimes you may in the future run into Heaviside notation written h of t minus c. You may see it written more like this. That's fairly common to see in engineering contexts. This is a more kind of universal context in mathematics and in information theory. So what we're going to do next is say, now that we figured out how we can turn on and off a function, what I really want to be able to do is start with a function, a known function, and then basically make it so that this function, just like it is right here, can turn on or off at any given time, right? So I want to essentially be able to take this function and shift it this way to turn it off or to turn it back on. So a little bit of a recollection from our pre-calc days, that if we plug in t minus a into a function, you're essentially taking the graph of f of t and you're horizontally shifting it. And if a is a positive value inside here, then you're shifting it to the right. And if a is a negative, you're shifting it to the left. So I want to be able to take a graph of a known function and multiply it, or not multiply it, but shift it one direction or another to make it graph. But just remember that if you take h of t and you let that be a u, I'll just use a number here, u of 4, u sub 4 times f of t, what you're essentially doing is this is suppressing f of t until t equals 4. So you're basically saying, I don't want to see the graph of f of t show up until t equals 4. The problem is that's not going to be the graph of f of t like this. It's going to be wherever 4 happens to be. So if 4 is like over here, then it will basically be flat line up until this point, and then all of a sudden the graph will start where it normally would have. What I want to be able to do is I want to suppress the function output, but also shift it to the right. So down here on the bottom, what I want to be able to do is take that same graph, it's the exact same graph as above, and just kind of suppress things and then shift the graph to the right. And the way to do that is to use what's called a shifted switch system. And so a shifted switch just makes use of the fact that if you were to take a graph g of t and write it as f of t minus c, that's basically shifting the f of t graph c units to the right. And then if I multiply that by u sub c, I'm essentially not only shifting the graph c units to the right, but I'm making it so that that graph doesn't show up. Nothing of the function shows up until t equals c. So it's 0 and then boink, and then it starts behaving like the f of t graph. So this shifted switch works only if this value and this value are the same. These must be the same. to count as a shifted switch. Because it's shifting by the same amount that the Heaviside function is delaying by. So we're going to play around with that as a possibility here and see how that might work. So let me move my notes down. And so on the next page, you can see our Heaviside function is going to work in a Laplace transform. So we're going to see what happens when we take the Laplace transform of the Heaviside function. Now on the surface it seems like, oh, this is going to be really complicated because the Heaviside function is a piecewise function. But remember, the Heaviside function is 0 everywhere up until a certain point in time, up until a certain value of t. So it's a really simple function up until the point where you get to a. So when we try to find our Laplace transform, remember it's e to the st times the function, and the function is 0 up until a. So we're able to make use of two parts of our integral. This first part is the integral up to t equals a. And of course, up until t equals a, our Heaviside function is worth nothing. It's 0. So that whole piece of the integral goes away. But that leaves us with everything from a to infinity thereafter. And everything after from a to infinity is really just e to the negative st times 1. So it's actually a really simple integral. It doesn't seem like it would be, but it is. This first part is 0. So we don't have to worry about that first integral. So we can go through the same rigmarole that we did before for a constant value and find out that the, that's what I'm looking for, the Laplace transform, there we go, of the Heaviside function just really depends on what that value is. At what point in time is the switch getting thrown? Because that point in time determines the value of your exponent on the output. This right here really is the Laplace transform of u sub a of t. You just have to know what a is. Oops, let me close my parentheses on the t. You have to know what a is, and then you can create the Laplace transform. Right? So what does that mean for us? Well, it means that taking the Laplace transform of a Heaviside function is actually really easy. But of course, things are not always just simple one function at a time. So let's practice a little bit down here. And again, my advice would be hit the pause button, try it for yourself, see if you can do these Laplace transforms, and then hit the pause button again to see if you got them right. So for this first one, we're taking the Laplace transform of the Heaviside function switching at 2. And we already know from up here that this is just going to be e to the negative a, in this case it's 2s over s. So that one was pretty easy, pretty straightforward. This one's a little bit more complicated, but remember, the Laplace transform applies linearly, so we can think of it as applying to each term. So this is really the same thing as the Laplace transform of 3 minus, and I'm going to pull the 2 out front, 2 times the Laplace transform of the Heaviside function switching at 2. So for the first one, that's just the Laplace of a constant, and we did that one in our classwork earlier today. We know that that's just going to be 3 over s. And the second one is minus 2 times the Laplace transform of this Heaviside function, which we know is e to the minus 2s over s. And that's it. That's all there is to it. So for these guys, they weren't too bad because we had a Laplace transform of really just a constant times the Heaviside function. But things can be more complicated. So for example, if you take a look at our table from before in the notes, you'll notice we've got our formula for the Heaviside function. but you also might notice that there are a whole bunch of other types of things that we're going to run into. The table is not exhaustive. It's not the only table that you'll run into. You can look up online Laplace Transform tables, and there's tons and tons of them out there, probably with functions that we've never seen before, never run into before. But Laplace Transform tables are pretty useful and pretty handy things. So the top of the next page introduces the concept of a shifted switch system. And what does it mean to take the Laplace transform of a shifted switch? Well, it's on the surface, it seems like it's going to be complicated, but really, if you know the Laplace transform of some function f, and that would be f of t, is big F of s. If you know that's true, if you know that to begin with, then you actually already know, or we know, how to deal with the shifted switch. The shifted switch, notice, this is taking the function that we knew to begin with, f of t, and shifting it to the right, if a is positive, a units, but at the same time also making it so that it doesn't turn on until a. So this is a classic shifted switch system right here. And it turns out, if you know the Laplace transform of the original function not shifted, if you know what its Laplace transform is, then the Laplace transform of the shifted switch is just the Laplace transform of the normal function times e to the negative as. So this, again, as a reminder, that the a value is the amount shifted. And this guy right here is the Laplace transform of the unshifted function, f of t. All right. So we're going to make use of that in an example here down below, so we can give this a shot. So we have an exponential, e to the negative t minus 3, and we're also multiplying it by the Heaviside function, u sub 3. And so you could probably tell just by looking at it that this is going to turn on when t equals 3, and this thing is going to behave like e to the t after t equals 3. So this really is a shifted switch already. It's written in the form, nice and easy for us to see. This is a shift of f of t equals e to the negative t, 3 units to the right, technically. And we can tell it's 3 units because it's right there and it's right there. It's the same value in, oops, sorry, let me scoot that up. It's the same value in the function, the adjusted, the transformed function, as well it is in the Heaviside function. So what we're going to do now is use our formula from up above and say, if we know the Laplace transform of the unshifted function. So we have to write this thing as e to the as, so e to the negative 3s times the Laplace transform of e to the minus t. That's the unshifted function, right? And so this corresponds to, here, I'm going to use a different color so it shows up a little bit better. This, the a value is right there on 3, and this corresponds to the Laplace transform of e to the negative t. And of course, the Laplace transform of e to the negative t is not terribly complicated. We can just hop back over to our Laplace tables here. See if I can find my Laplace table. Where did I put it? Oh, I've got it right here. Too many papers to hold on to. The Laplace transform of e to the negative t, that would be with a is equal to negative 1, so this would be 1 over s plus 1. So this would be 1 over s plus 1. And of course, just to be on the safe side, we have to remember that this is true for s values that are greater than the negative 1, right? That comes from the restriction on that Laplace transform. So we can think of our shifted switch formula up top as if there's a way to imagine, if you've got a shifted switch or the possibility of a shifted switch, making it so that this A value and that A value are the same, and being able to see what the unshifted function would therefore look like. So we're going to see some examples of that. But down at the bottom here underneath, I'm just going to say remember, we can undo a Laplace transform. With inverse Laplace. And it's easy to do that on Maple. So we can always double check ourselves before we double wreck ourselves. So if I go back and I say, hey, what is the Laplace transform of e to the minus 3s times 1 over s plus 1 in Maple, if I say give me an inverse Laplace for e to the minus 3 times s, that thing times 1 over s plus 1. Maple can help us. And again, we're going to be converting that or inverse Laplacing from s back into a function of t. And Maple says, let me think about it. Oh, that is Heaviside t minus 3 times e to the negative t plus 3. And take a second and convince yourself that that really is the problem that we started with. Heaviside of t minus 3, that corresponds to e to the, u with a subscript of 3 times t. And e to the minus t plus 3 really is the same thing as e to the minus t minus 3. So we got exactly what we put into it. So undoing the Laplace, we wind up exactly where we started, which is a good thing. So I'm going to end the video here. We've got some more examples to take a look at, but I'm going to end the video right here.